The pressure that keeps an astronaut alive in vacuum inflates the suit against every movement, turning every bend of a finger or elbow into a contest against a pressurized shell. And across a 6-hour EVA, that contest produces the kind of cumulative physical damage that has ended careers and will outlast the mission on every planetary surface where NASA plans to send people next. The photographs never show this part. The Artemis suits, the ones released to media, reproduced in every article about the moon return, show articulated gloves, reinforced palms, precision fingertip material for delicate tool handling. They show what the suit was designed to do. They do not show what the suit is doing at hour 5 of a 6-hour EVA to the tendons behind those fingertips, or what the forearms inside those gloves have been running against since the moment the suit pressurized and stopped being clothing and started being a contest. Outside the suit is vacuum. Nothing. No air, no pressure, no resistance. Inside the suit, the air pressure is maintained at roughly 30% of what you breathe standing on Earth right now. Low enough to feel thin at altitude, but high enough to keep blood from turning to gas. That 30% is the threshold. Drop below it, and the fluids in your body, not just blood, but joint fluid, saliva, the moisture lining your eyes, begin to boil at body temperature. Not boil dramatically, boil silently and everywhere, the way a carbonated drink loses its gas when you open the cap. The suit holds that pressure inside a flexible shell, and a flexible shell holding pressure against vacuum behaves like a balloon, not metaphorically, physically. It inflates, it stiffens, it resists every attempt to change its shape, which means it resists every movement of the body wearing it. That is not a design flaw. It is what pressure inside a flexible container does. Imagine putting on a pair of rubber dishwashing gloves, then having someone inflate them slightly with air before you try to use your hands. The material is still technically flexible, your fingers can still technically move, but every bend fights back. Every grip requires force not to close your hand, but to compress the air inside the glove at the moment of the bend. Relax your grip even slightly, and the glove springs back toward open. The gloves are not heavy, they are not painful, not yet, but every single finger movement costs something extra, and after 10 minutes of repeated work, the hands are tired in a way that feels completely out of proportion to what they actually did. Now hold that for 6 hours. The average force required to close a fist fully inside an EVA glove operating at life-sustaining pressure is somewhere between 4 and 9 kilograms. Which means gripping a standard handrail, closing a sample bag, or squeezing a drill handle costs roughly the same muscular effort as compressing a moderately loaded spring. Not heavy, not impossible, just constant. Every closure of every finger against the glove pressure is that spring. And across 6 hours of surface work, that spring gets compressed thousands of times before the EVA clock reaches 0. The grip force number is not the problem. The number of times it has to be applied without rest is what the tendons remember. 100% of astronauts who have completed a full-duration EVA have reported hand fatigue and discomfort. Not a fraction, not the ones with smaller hands or weaker grips. Every person who has worked inside a pressurized suit for a full EVA shift. The result is not anecdotal sensitivity. It is the universal reported experience of the suit doing exactly what physics requires it to do. Between 2022 and 2023, NASA's EVA hardware team documented a specific pattern in ISS long-duration EVA records. Multiple crew members had experienced fingernail delamination, the partial detachment or complete loss of fingernails after repeated long EVAs. The mechanism was direct. Pressing operating pressure forced the glove material firmly against the hand throughout the EVA, and sustained contact between the glove interior and the nail bed across multiple hours produced subungual hematoma, the same injury a heavy door produces when it catches a fingernail in a door frame. Not once, not from a single incident, from the cumulative pressure of the glove pressing in the same place thousands of times across a shift. The hardware team issued a formal recommendation to modify the glove interior geometry to reduce contact pressure at the nail bed. The modification was tested. It worked within limits. It reduced nail bed contact. It also added measurable resistance to fine motor tasks inside the glove because the liner thickened the interior space and reduced the precision of fingertip contact. The fix for the injury made the hand slightly less useful. Both outcomes were documented in the same report. The liner is thinner now. The nail bed still contacts the glove. The pressure that presses the glove against the nail bed has not changed, because the pressure required to keep the astronaut alive has not changed. The obvious answer is to reduce suit pressure. If the spring that fights every movement is inflated by the operating pressure, then lower the pressure and the spring softens. The engineering is real. Suits have been tested at lower operating pressures and the joint resistance does decrease. Moving the fingers is easier. Closing a grip takes less force. The physical toll across a 6-hour EVA drops. This part of the logic holds. What drops with it is the safety margin above the threshold where blood begins to gas out. The threshold is fixed. It is a physical property of body fluids at body temperature, not a standard that can be adjusted, not a limit that engineering can move. The suit operates above that threshold specifically to prevent blood gas emulsification in the astronaut's circulatory system. The gap between operating pressure and the threshold is the margin. Reduce operating pressure to ease joint resistance and the margin narrows. A suit leak that would have given the crew member minutes to reach the airlock at standard pressure now gives them less time. A slow pressure loss that would have been survivable becomes lethal faster. The astronaut's hands are easier to use, and the astronaut is closer to the threshold at every moment of every EVA. The pressure that was grinding down the tendons was doing so while maintaining a buffer. The softer spring comes with a thinner margin, and on planetary surface 400 kilometers from any possible rescue, thin margins do not accumulate without consequence. This is the bind that every suit engineer working on Artemis and every Mars architecture is already inside. The failure that follows from a standard 6-hour Martian surface EVA does not begin with a catastrophic event. It begins with the first EVA completing normally. Grip strength reduced, forearms fatigued, tendons carrying a load they will not fully shed overnight. The second EVA begins from that baseline, not fresh, not recovered, slightly degraded in a way that a fit astronaut in training can compensate for. The third EVA starts a degree below the second, the fourth a degree below the third. By the end of the second week of daily surface operations, the hands operating the drill, the hands assembling the habitat connector, the hands that are required to apply controlled force to geological samples and pressurized fittings and surface anchors, are working from a reserve that each EVA day has drawn from without fully restoring. At some point in that progression, not day 2, probably not day 5, somewhere after a week of accumulated load, the inflammation in the finger tendons stops responding to overnight rest the way it did on day 1. This is not speculation. It is the clinical pattern of repetitive strain injury in any occupational context where the same tendons apply force against resistance for extended shifts with inadequate recovery. The tendons of the fingers and wrist are among the most load-sensitive connective tissue in the human body, and they have a recovery window that is measured in days, not hours, when the damage is cumulative. The mission scheduler looking at a Martian surface operation as a fixed surface stay. The orbital mechanics that brought the crew to Mars will take them home on a specific window regardless of the state of the crew member's right hand. There is no option to delay the surface EVA schedule by 2 weeks while tendons recover because the surface stay was already calculated to the day before launch. The EVA schedule does not pause. The tendon inflammation does not pause either. EVA Day 17. The habitat connector needs to be torqued to specification before the next dust event covers the worksite. The crew member applying the wrench has been closing their fingers against glove pressure for 17 days. The torque value is not above the crew member's maximum grip strength. It was not above it on day 1. On day 17, with the forearm tendons carrying 17 days of accumulated resistance load, it may not complete without tearing something that was not torn on day 1. The drill work continues. The mission continues. The biology does not receive a memo. The mechanical counterpressure suit has been the theoretical escape from this problem for more than 30 years. The concept is precise. Instead of surrounding the body in a gas-filled shell that inflates against vacuum, you compress the body directly through a skin-tight elastic garment. The compression is applied through contact with the skin rather than through pressurized air, which means there is no gas volume at the joints to resist deformation. Bend the elbow inside a mechanical counterpressure suit and you compress elastic fabric against skin, not a pressurized air column against the joint. The spring is gone. The resistance drops dramatically. The hands can work. Research programs at MIT and other institutions have demonstrated that the concept produces real, measurable reduction in joint resistance at the pressures needed for EVA. That part works. Applying uniform pressure to the full surface of a human body through a garment that can still be put on and taken off without assistance in a habitat has not been achieved in more than 30 years of trying. The human body is not a geometric shape that yields to a single elastic tension formula. Ankles, armpits, the webbing between fingers, the concave curve of the lower back. Each surface presents a different geometry, a different tissue compliance, a different response to compression. A garment tight enough to pressurize the forearm adequately leaves the armpit underpressured. A design that solves the armpit creates a pressure point at the collarbone. Every solution at one surface creates a deficit at the adjacent one, and the consequence of an underpressured patch on a mechanical counterpressure suit is not a gradual warning. It is localized ebullism. The tissue at the low pressure spot begins to swell with released gas from the fluids underneath it, which arrives quickly and without the warning time that a conventional suit leak provides, because the failure is local and the rest of the suit is still functional. 3 decades, multiple funded programs, a shelf of research papers showing the physics is sound in principle, no qualification for planetary surface EVA. The Artemis suit, the Axiom space design, the one that will carry the first crew back to the lunar surface, has articulated joints, convoluted pressure sections at every major bend, an engineering iteration that drew from decades of Apollo and ISS EVA data. It is genuinely better than the suits of 40 years ago. The joint resistance at the glove is lower than it was. The forearm fatigue after a 6-hour EVA is less severe than it was in 1972. That progress is real, funded, and tested. At the end of Artemis 3's first lunar surface EVA, the crew members' hands will still be fatigued in a way that has nothing to do with the work they were asked to do, and everything to do with the pressure holding them alive. Every documented EVA crew has reported this. The engineering has not removed the report from the record. It has made the number in that report somewhat smaller. Any flexible suit maintaining pressure against vacuum resists movement at every joint, and that resistance scales with the pressure required to keep the wearer alive. The Mars surface mission, currently in concept planning at NASA, schedules EVA operations that will require more cumulative suit hours per crew member than any lunar mission in history, by a factor that makes the ISS EVA record look brief by comparison, and without the option of shortening the surface stay once the crew has committed to the surface. The crew will be operating against the same balloon physics that delaminated fingernails on the ISS and fatigued hands on the Moon, across a stay duration that will find the outer limit of what human connective tissue can absorb inside a pressurized glove. The suit that keeps them alive is the suit they will be fighting every hour they are on the surface. What the mission planners have not publicly answered is this: at what point in the EVA schedule does the cumulative tendon load in the crew's hands exceed what can be managed through task modification and rest scheduling? And what happens to the habitat assembly timeline when that point arrives, 8 months from the nearest hospital, with the next launch window fixed on the calendar regardless of what the crew's hands can still do?